a slightly different TADS talk in the sense that Sumon is using this time to both give a TADS talk and also do his research proficiency talk, which is an oral presentation that is given in our department. So the format of this talk will be the usual. That Sumon will give a 40 minutes presentation, and then we will open the floor for Q&A for about 10 to 12 minutes, and then if others have questions, they can stay after and ask Sumon any follow-up questions. So with that, I would like to go ahead and get introduce Sumon. So Sumon Biswas is a PhD student in the computer science department at Iowa State. His research interests are the blend of software engineering, data science, and program analysis. He has worked on large-scale data science program analysis using the VOA framework. He is currently contributing to the Dependable Data-Driven Discovery project. Specifically, he is conducting research on improving the fairness of machine learning models. So with that, Sumon, if you could go ahead and get started, please.
Sure. Thank you, Dr. Rajan. Today I'm going to talk about my recent work, which is to the machine learning models on a crowdsourced platform exhibit bias. So this is an empirical study to understand model fairness, how models are predicting, and how the decisions of the models are fair or not. So this work has been accepted in Foundation of Software Engineering Conference 2020. So that will be in November 2020. So yeah, with that, I'll start. So what is software fairness? So a software is unfair when it discriminates between people. So here we will talk about the societal discriminations. In our software, if we are analyzing data of people and there are protected attributes like race, sex, age, or religious beliefs, then our software, if our software prediction is dependent on those protected attributes, and if different groups in those protected classes are discriminated, then our software is not fair. So here, like for an example, if we are approving loans with our machine learning models, and if our software discriminates between men and women, with the similar attributes, if men are getting their loans approved and women are not, then we will call our software unfair. Basically, male and female, those are different groups inside the sex protected attribute class, and we will call some groups inside that protected class privileged, who have been seen and who have been seen to get certain systematic advantage historically. Like men have got some privilege in model prediction. So why the fairness of machine learning models? Basically, we have been looking on the dependability of data-driven software for a little bit long time, like different properties of data-driven software, such as the uncertainty or data freshness, and fairness is also another property of data-driven software. And we have seen a lot of like data-intensive software is being used in real world, like credit approval or hiring employees or making admission decision for the applicants, or maybe in a company. And also we have seen like using those software in criminal sentencing. And recently, many of these software have been reported to discriminate between societal groups. So next, I'm going to talk about some incidents that we have seen recently. In the first example, we can see that so Amazon actually started their same-day delivery in many cities, but they have bypassed some zip codes, zip code of many areas where most of the people are African American. In the second example, we can see in 2015, Amazon used a secret AI tool. So that tool was intended um, to classify or to filter their job applications. So and the tool was reported to discriminate between men and women. Especially the recruiting engine was penalizing the resumes of women, and with the same qualifications, women are being penalized and men are not. So then Amazon decided to decided not to use that software anymore. Uh, in the left side, we can see Google Translator was so when we are translating these two sentences from English to Turkish, and then again back from Turkish to English. So Turkish is a language where there is no separate pronouns for male and female. So when we are translating from English to Turkish and again um, Turkish to English, we have seen that the pronoun she has been assigned to the nurse and pronoun he has been assigned to the doctor. But in the original sentences, it was reverse. In the example in the right, the Guardian actually reported that Google discriminated showing job advertisements to men and women, and they have done an experiment which showed that like the high-paid job advertisements are have been shown to men 1800 times, but and the same job advertisement have shown to women only 300 times. So it's like 6 times more to men than women. So this is another discrimination. So this software has been discussed a lot in recent past. So Compass is a software developed by Northpoint, which predicts the criminal activity of people based on the policing data. This software has been used in at least 12 states in the United States, like New York, Wisconsin, California. And what that software does is yeah, based on their previous criminal activities, it predicts a score, a risk score of how is it likely that person is going to commit another crime. So in the left side, you can see the photo of two people. So the left person has been assigned low risk, only 3. So this score is basically from 1 to 10, and the right side person has been assigned high risk. But if we analyze their previous records, like we can yeah, if we analyze their previous records, we can see that the left person has 2 armed robberies and 1 attempted armed robbery, but on the right side person has 4 juvenile misdemeanors. So this is clearly a discrimination. And so the right person has only 4 juvenile crimes, but she has been assigned a very high score compared to the left person. And if we look at the overall risk, we can see that the African American 44% of the African American actually labeled higher risk, but they did not actually reoffend, whereas the percentage for the light-skinned people are only 23%. And if we look at the people who labeled lower risk and yet did reoffend, we can see the discrimination, the similar discrimination happens there. Like 47% of the white people has been labeled lower risk and yet did reoffend, but only 20%, 8% of the African American people have been labeled lower risk, but they reoffend. So this is a very crucial, so machine learning models have been used in very crucial softwares nowadays. So, and we have found like many more examples like this, like Google fixed their image classification software where they found that they have been classifying dark-skinned people to gorillas, and then Facebook has been accused to show advertisements to different specific people. And if you are using Mac, then advertisement, your hotel price is higher than others. Like Facebook, Amazon, or T-Mobile, they have also alleged age discrimination in Facebook job ads. So with this, we thought that it is very important. We understood that this is very important issue, and we need to investigate more to understand how software are being used and how fair are their decisions are. So several work already has been done on this topic. Basically, 3 communities have done research on this topic. Mainly, many research has come from the ML community. The machine learning algorithms and metrics have been proposed. Machine learning community who proposed the theory and measures of unfairness. A few bias mitigation algorithms have also been developed from the ML researchers. In the second, many research has been done by the HCI community. The human-computer interaction research has been done to interview many people and survey and research on ethical aspect of fairness of software. And third, recently, software engineering community has also focused on this issue, and mainly some papers has been published on testing the fairness of software. So basically, generating automated test cases and detecting bias in software. We are the first to work empirically on software engineering aspects of bias, mitigation, and impacts. So we have tried to see if the practitioners models, so the models developed by practitioners in the real world are showing bias, and also we try to mitigate those bias using the well-known techniques from the first prior works. And then we have seen what are the impacts, like if those mitigation techniques can actually work on work to mitigate the bias, or they are still showing bias, and how the performance changes after applying the mitigation techniques, and so on. So this is our overview of our work. We have actually created a benchmark of ML models from wild, and then we have answered the following 3 research questions. Broadly, we have measured the unfairness. What are the unfairness measures of ML models in the wild? And then we have asked what are the root causes of the bias. We try to see what is causing the bias and which techniques actually successfully mitigate the bias. And if there is any pattern, we have also done some comparative study to look at different classes of data sets, tasks, and how different mitigation techniques are related to the fairness. And finally, we have seen, after applying the mitigation techniques, what are the impacts, like what are the performance changes, or if the prediction is still valid or not. So this is the process and description of our benchmark. So our aim was to look at the machine learning models from wild. So we have collected actually models from Kaggle. So Kaggle is one of the most popular data science platforms where one can host a competition and take part in competitions. So Kaggle is basically owned by Google. Until now, there are more than like about 400 competitions in Kaggle, and each competition offers some prize money, and you can participate in the competition in a group or individually. Also, apart from the competitions, users and organizations also upload their data sets on Kaggle, and until now there are more than 30,000 data sets on Kaggle. And now when we are looking for models from the Kaggle, all of the tasks are not appropriate for fairness studies. So we looked at the uh, previous previous work and data sets which have been used to uh, measure fairness and do fairness studies. So we have taken two different we have taken two different process to collect models. First, we have looked at the previous work, and we have found the data sets which have been used. Like you can see these three data sets: German credit, adult census, bank marketing. These data sets have been used. So we have found some more data sets in the literature, but those are not available on Kaggle. So first we went to the literature and then collected the data set, and we have seen if those data sets are available on Kaggle, and then we have collected the models people submitted for those data sets. The another approach was to see what are the well-known protected attributes. So we have seen that this list, race, color, national origin. So these are the protected attributes which is listed by US Congress Equal Opportunity Act. And we have looked at all the competitions, all the 400 competitions, and we have seen which competitions are using actually one of these attributes in their dataset. From those, we have also collected like 16 models. So two different categories, two different tasks, and 16 models. So in total, we have 5 tasks and 40 models. So these are different 5 tasks. German credit is basically like data of people. This dataset contains personal information about individuals and predict actually credit risk, if your credit risk is good or bad. Here, adult census, actually the second one. So this one comprises of individual information from US census. Here also we predict whether an individual earns more than $50,000 or not. And the third data set contains marketing data of a Portuguese bank. Here the goal is to predict whether a user subscribe for a term deposit or not. This one is also financial data, and this data set contains data related to loan applications for individuals that actually the individuals don't have credit histories, or they cannot get loan from traditional banks. Here the target is to predict whether an individuals will repay the loan. And finally, we have the Titanic machine learning dataset, and this dataset contains data about passengers of the Titanic. The target is to predict whether the passengers survived the sinking of Titanic or not. Here, the protected attribute is 6. So on these 5 different tasks, we have collected 8 models from each of these tasks, and then we have done our fairness analysis on this data set. So what are the fairness measures? How do we measure the fairness? Many fairness definitions have been proposed in the literature recently. So basically, we have 2 different categories of um, fairness measures. One is the group fairness, another is individual fairness. So group fairness is, as the name suggests, measures the fairness among different protected attributes, protected groups. For example, if sex is the protected attribute, then we should evaluate whether the prediction accuracy is similar for men and women. And for individual fairness, on the other hand, it does not consider groups. It is also called the counterfactual fairness. If any two valid inputs that only differ in protected attribute, and if they receive the same label in the classification, then we call the model is fair. And to define the next, we will be discussing the fairness metrics in each of these categories. But to do that, we have to also fix what is our privilege group. So when we have we will calculate the group fairness, we have to fix that which one is our privilege group. If we say race is our protected attribute, and there are whites and American Africans or Latinos, then we have to say which group is the privileged group historically, who got the systematic advantage. And then we have to fix the favorable outcome. So each task has some outcome or the prediction level, and we have to fix that which classes or which an outcome are favorable. Like for German credit risk, if the credit is good, then we say that is favorable. Or in adult census, if the income is more than 50,000, then we say that this outcome is favorable. But if certain individual is classified as they have income less than 50,000, that is not favorable. So this we fixing the privileged group and the favorable outcome is necessary to define the fairness metrics. These are the fairness metrics we actually used in our study, and there are 7 metrics here, 5 from the group fairness category and 2 from the individual fairness. And yeah, so actually many other metrics have also been proposed in the literature. We found a recent paper described 21 different metrics and that have been used to measure fairness. So different metrics also describes a different definition of fairness. So we actually used a comprehensive set of metrics from a paper, and we have added some other metrics to which have been recently proposed, like consistency, and then we have used all of these metrics for we have measured all of these metrics on each of the models to see to find all different kind of biases they exhibit, and also find some trade-off between different metrics. Disparate. So also some of the metrics are based on the ratios, and some of the metrics actually measures the differences. So for example, if you look at the first one, so this is the most popular, and most of the paper are using this disparate impact. So this is so in these equations, actually x y are the y cap is the prediction level, and y cap is 1 if the prediction is favorable, and z is the protected attribute. Z equals 0 if this is unprivileged class, and z equals 1 if this is the privileged class. So this is basically the ratio of the probabilities, if whether the unprivileged gets the favorable outcome or the privileged gets the favorable outcome, and this is the ratio between those two. And if you look at the SPD also measures basically the same, but instead of taking the ratio, it actually measures the difference between these two. EOD, that actually accounts for the true positive rate from the unprivileged. So this is the true positive rate of the unprivileged group, and this is the true positive rate of the privileged group. and then it takes the difference between that two, and that is their fairness measure. Average odd difference is also, apart from true positive rate, it also accounts for the false positive rate. So basically it takes it measures the difference of unprivileged and privileged rates, and then uh, it takes the mean. Error rate difference, instead of taking the positive rates, it also um, accounts for the negative rates, like the false. The error rate is basically the sum of false positive rate and false negative rate, and error rate difference is the error rate of unprivileged minus error rate of privileged. These two also measures, defines these two equations and measure the individual fairness. So next uh, we will actually measure each of these metrics on each of the models, and then we will try
That's
to.
a question.
Yeah, sure.
So in your matrix is only conditional on z equal to 0 or 0 equal to 1. How about the other covariates? Are they not considered at all in this kind of matrix?
Yes, actually, when like in the first one, they only considers. Oh, okay. So if you're saying z equals other values, right? So here they have transformed all of them into privileged and non-privileged. So like if there are many classes in race, white, non-white, and Latinos, then they have only taken one as privileged. So one versus all classification. Uh, so white has been classified as privileged and others have been non-privileged. So z equals 0 means non-white, and z equals 1 means all the whites.
Yeah, I understand that. So, but I thought when you are talking about, for example, credit risk, right? So it does not only depend on the race, it's also dependent on your financial situation and other things. Usually, if you are trying to do a model, you also want to adjust for those. So when you are talking about fairness, what you want to claim is that after adjusting for those, for example, the people with a certain group are still being treated unfairly, right?
Mm-hmm. Yes.
I'm not sure if all those kind of variables are entering into this index, or they are not considered at all. So
Yeah.
marginally, for example, if one group is much lower income and they have a lot of other factors and will be considered a higher risk, you have to adjust them before you assess the fairness issue, right?
Right. Actually, there, when the classification model works, that actually takes account all of the features. But when we are talking about fairness, we only look at the protected attribute feature, and we see the rate difference in those feature, those classes. Like if the male has the accuracy 90% and female got the accuracy regardless of what other attributes. If the male has the accuracy 90% and female got the accuracy 60%, then your model has to be unfair. So maybe your data is unfair, or you did not collect enough data for men. So maybe the machine learning model uh, is taking account all the features, but still when these fairness metrics are measured, they actually considers the protected attributes.
Okay, go ahead.
Yeah, okay, yeah. So next we actually uh, apply different mitigation algorithms on these models. So basically there are three kinds of mitigation algorithms. The first one is pre-processing algorithms. So those actually operates on the training data, and that does not change your prediction level or does not change your model itself. It changes the uh, training data and the weights of data, etc. And in processing algorithms, so that actually changes your model and applies new techniques to or different techniques to measure different feature and remove the bias. And the post-processing algorithms are applied on after the training, and they actually can change the prediction levels. And when the model is done with their prediction, then it can change the prediction and then to make the decisions more fair. Yeah, so we have actually used 7 different mitigation algorithms from the literature. So reweighing actually changes the weights of the training data, and disparate impact remover edits the feature value to improve fairness, and 2 different adversarial debiasing actually uses adversarial technique to maximize the accuracy and reduce the evidence of protected attribute. Prejudice remover also uses a regularization or discrimination algorithm, and these 3 actually modifies the predicted level, or it actually finds the optimized level of probability based on which it can change the prediction level so that the accuracy is not harmed, and also the fairness metric is optimized. So this is our experiment design. Basically, for each of the model, we evaluated all of the fairness metrics that we described, and then we applied.
Sumon, can you go back to that previous slide, please?
Yes.
So it looks like in the pre-processing and in-processing algorithms, these attributes, the protected attributes, are actually in the data.
All right.
While these algorithms are being developed and trained, is that correct?
Yes, the protected attributes are in the training data. Yes.
So simply removing
yeah. So actually,
attributes from the data, that's not a mitigation algorithm or mitigation strategy.
No, actually, we have seen that many theories have been proposed. Theories have been presented that shows that only removing the data is not an option, because there are many correlated attributes also. So if we even if we remove the protected attribute, the bias also remains, and we need further mitigation algorithms, and only removing actually does not work.
But then it seems like Zheng Wan's question is more relevant, because you're accounting for these protected attributes in the training algorithm and the model development, but then you're not accounting for them when you're measuring the disparate impacts. That seems like you're not really measuring the disparate impacts in a way that's consistent with the way that you're developing the model, or the model was developed.
That is correct. Actually, when we are measuring the fairness, these metrics they actually don't take account of these measures, don't consider the other features. But since all the features are contributing to your decisions, we actually need to investigate, or we need to, when we mitigate, we need to consider all of them. But yes, that is, I think for this reason, this is a very difficult problem. And also, when someone is measuring fairness, they are not considering other things and only looking at the protected attributes. But yes, I think that is a valid point.
Okay, thank you.
Okay, so we actually, for each of the model, we evaluated the performance metrics like accuracy and F1 score, and then we have for each of the model, we applied each of the mitigation algorithms. And after applying the mitigation algorithms, we evaluated our performance and fairness metrics again. Then we and for each of these metrics, we actually run it 10 times to see if the metrics and the performance are stable or not. And we use the same pre-processing techniques for each of the data set to see the effect of the model, so that the pre-processing techniques don't affect in the fairness. So next we are going to talk about the fairness results we got. So here we have plotted all the fairness metrics for each of the 40 models. And here, these are basically different dataset categories, each of 8 models in each of the dataset category. We can see it follows the similar pattern for the datasets, and we have found the data is the main reason of unfairness. If data is unfair or imbalanced, or maybe the protected attribute is contributing more to the prediction, then regardless the different model constructions, it actually shows a similar pattern. And we are going to talk about a few instances where we have seen the fairness is low or very high. So also we have seen over the 10 runs, most of the fairness metrics have been consistent. So these are 2-3 metrics where we have seen the metrics are not so much consistent. And if we look at the data set, if the data set is small, like the number of instances is low, then it is more inconsistent. Like before each of the training, we actually shuffle the data and then split the train and test. So if the data set is large, then there is even after shuffling, the data set remains persistent. That's why you can see the home credit. So this data set is very large. So in this case, this is more persistent. And we have seen DI, so disparate impact, has the blue lines has been more. So basically here we have plotted the standard deviation. So standard deviation is high. That means this has been more not very consistent. So DI has been the most inconsistent, because DI actually the only one that measures the proportion of 2 probabilities. And even if the proportion is not very different between privileged and unprivileged group, the ratios can be very high. That's why it is more sensitive, sensitive metric. So also we have taken, oh, I forgot one thing. So basically, if the fairness value is less than 0, it is biased towards the privileged group, and if it is positive, then it is biased towards the unprivileged group. And if it is close to 0, then it is fair. So our goal is to actually make everything close to 0.
So
yes.
Ask. So you have GC, AC, BM. These are different data sets, right?
So these are models, name of the models, and these boxes are same data set. So German credit.
Yeah. GC 1, 2, 3, 4, 7. The 8 are the 8 different models.
Yes, right.
You have 5 data sets.
Yes.
So no matter. So basically, what you say that is the BM and the HC has some bias problem. The other 3 are not. Is that right, or how do you interpret?
So yes. So if you look at this BM 1 to 8, we can see this BM 5 is more fair than others. It has less bias in terms of most of the metrics.
Okay. But for the other one, like GC and AC, there's no problem.
No. So all of them actually showing bias. And so whenever so for each, so if you look at one of the metric like GC2, if there is anything, any metric that is bigger than 0 or less than 0, that is the problem. So actually, when the metric is, and the value is 0, then it is fair. And anything above 0 and below 0 is unfair. So all of them.
You cannot get it exactly 0. So you got to have some kind of indication of whether they're significantly different, right?
Yeah. So we need a good threshold, like when we are going to call it fair and unfair. So when it is close to 0, basically it's fair, but when we are stop calling it, I mean, a good need of threshold is has been understood. And also to compare between these models, we have also taken the absolute value and plotted the sum of all the metrics, and also calculated the accuracy and F1 score. So here we have trying to compare that which between these two models. We can see this one has a low bias, so close to 0 means low bias, and this bias is higher than this one. So here you can see between GC1 and GC2, GC1 is much fairer than GC2. Also, in most of the cases, we have seen that fairness has a cost. Like whenever some model is becoming fair, it is losing some performance, like accuracy. But in some cases, we have seen that some models are fair as well as um, they are retaining their accuracy. Like AC6, between these all adult census models, this has lower bias than most of the other models, but it has also the more accuracy than most of the other models. So yeah, next I'm going to talk about some of this. This was a very interesting observation. We have seen that most of the developers are trying to optimize their models based on the accuracy. This is very understandable. But while they are optimizing for accuracy, they are introducing some model constraints which are affecting the fairness a lot. Like GC1 and GC2, if you compare, the bias of GC1 is much lower than GC2. GC6, and we have seen the both of the models are using the random forest classifier, and they have done some grid search over some parameters, and we have experimented with those parameters, and we have seen that the main difference is given by the scoring function used in the grid search. Basically, GC1 has used recall as the scoring function, and GC6 has used precision as the scoring function. And we have investigated the data set, and we have seen that after the classification, there are a lot of false negatives, which are actually the data of women. So when we are optimizing for recall, we're actually trying to lower the FN, false negatives, and in that case, since the number of false negatives, the percentage of women are more than men, then trying to optimize with recall actually balances a lot of, removes a lot of bias. So, but the main goal was to optimize for accuracy, but we have seen that optimizing for recall actually giving a lot of better fairness. Yeah, and also another implication is this recall, optimizing for recall is for overall data, but not for specific classes. But fairness actually looks, fairness metric actually look for the true positive rate or false negative rates of different classes. So if we could actually optimize if the model constructs could provide some optimization inside different subclasses like male or female. If we could optimize true positive rate of the male, true positive rate of female, then we could develop much fairer models. So optimizing for different subclasses would be intended here. So here, if we compare these two models, AC1 and AC2, here these two models have used this light gradient boost model classifier, and AC2 has been seen largely, so this DI is very high, and this is biased towards privileged group, and this is biased towards unprivileged group. So both are using the same classifier, but they have a very different difference in their fairness. We actually found that AC1 has used this class weight balanced. So by using that, it has balanced it the weight of each class. So basically, if there are imbalance in the data set, like in this data set, we have seen that 66% of the data items are female and 34% are only male. So there are a lot of imbalance in the data set. And if we try to balance the weight of each data item, like how much it is contributing to the prediction, then there could be a lot of difference in the fairness. Also, another thing is the model construct, this class weight balance, this is affecting the fairness directly, but the library developers also do not mention anything about fairness, and since developers are always trying to increase the performance, but they do not understand what could be the effect on different classes for using different model constructs. It necessary to document those things as well.
Sumon, I have a question. Is this the TI index between HC1 and HC2?
DI. So DI.
Oh,
yes.
Okay. Because that TI index, the scaling by 1/n seems wrong. It's like an entropy measure. You'd expect it to be scaled by log n. And I notice in your HC1 and HC2, your n's are quite different.
Yes, that's correct. So the TI is actually the rightmost one, and it actually almost the same. So we did not investigate the TI much here.
Okay,
so, yeah. So this is the disparate impact difference that we found.
Yeah. Okay.
Okay. So
I wanted to remind that we are close to running out of time. So if you could please.
Okay, Professor, I'll finish quickly. So another thing is we have found that scaling features would be very desired in terms of removing bias. Like in this data set, the bank marketing data set, we have found that so this is the age distributions, and if the age is less than 25, we have categorized it as younger, and more than 25 has been categorized as old. So basically here actually 95% people are older, and so it has been actually encoded, use the one-hot encoding. So the value of the age column has been close to the mean. The mean and standard deviation was very, so mean actually was very close to 1. So it was affecting the classifier more. But BM5 has used the standard scalar technique, and this technique actually scales all of the features and brings all of the features into one scale, like the same mean and same mean. So so a specific feature cannot contribute to the prediction more. That's how they actually the BM5 was much fairer than all others BM models. Dropping a feature actually also helps. We have seen, so between these two models, one has used all the features and one has dropped the number of years of education of people. So this dropping a feature, so basically one feature was affecting the fairness. So when the model actually dropped one feature, it was more biased, the AC5. We also seen that different metrics are needed because like for this model, if we only consider DI, then then we can see that this BM5 is better than all other models. But if you have considered only ERD, then we have found that the ERD is more than any of the other models. So since different metrics are has different definitions and they are not very consistent with each other, we need actually uh, more research, and we need to understand all of the, we need to measure many metrics. Also, we have seen that the correlation of the metrics actually don't follow much on when we are following two different data sets. Yeah, so a fair model with respect to one protected attribute might not be fair with respect to another protected attribute. And then we have applied the mitigation algorithm. So basically this is before mitigation and this is after mitigation. We have selected the best mitigation algorithm for each of the model and they plotted the same graph, and we have seen that many mitigation techniques are very successful, and we have done some analysis on these. So here you can see most of them are basically from reject option classification or calibrated equalized odds. So basically the last three are post-processing techniques, and post-processing techniques have been actually more successful. So, and also we have seen reweighing. So basically the pre-processing techniques have also been successful in many cases, and we have concluded that pre-processing techniques might be more desirable because it retains the performance in every time. But in these cases, the reject option classification has been more successful, but it cannot retain the performance. It has lose many accuracy and F1 score values. So yeah, and models in the same dataset category actually follow the same kind of mitigation techniques becomes successful. Yeah, I've already discussed this. And we also analyzed like which mitigation techniques are better for which kind of data set. And we have found that the models, so these are the for least biased models, and these are the most biased models. And for the most biased models, we have seen that post-processing techniques, so this is the rank. So if the rank is very low, then it is the most successful. So the post-processing techniques have very low rank for the most biased models. But for least biased models, we have seen that pre-processing techniques are successful. So basically, if the model is having a lot of bias, then post-processing techniques might be good. But if it is not having much bias, then pre-processing techniques is good. So yeah, I'll go. So this is the summary. Basically, we have found ML some work needed in the ML libraries need to implement fairness specification, and we have also discussed found some data set and feature scaling techniques to remove bias. And about the metrics, which metric to use is a very important question, and that is not a clear answer. And often there is a trade-off between performance and fairness. And about the mitigation techniques, pre-processing algorithm will be preferred because it retains the performance, and post-processing effective, but it often does not actually retain the performance. Yeah. Finally, I can tell that there are a lot of other challenges like legal, ethical, or trust issues, and also what is the human perception of the fairness. Only mathematical representation of fairness is not enough, and determining good threshold for each of the values is also important. We have some future also directions to extend the work from the classification technique to multiple classifications and also the ML pipeline. So this is the summary what I presented today. So thank you. Do you have any question? Please ask.
Thank you very much. Thank you very much. That was wonderful. I appreciate that, Sumon. So we can probably stop recording at this point and have a Q&A.
Yeah.
I feel that this definition of unfairness is a little bit misaligned with the purpose, that you basically define the accuracy within each subgroup as the fairness. Well, accuracy is not equal to fairness. You could, so that's the whole thing. I don't quite understand why this is defined in this way.
Yeah,
it
so,
has something to do with, but it's not equivalent, right? The accuracy could be, the difference of accuracy within different groups could be resulting from different reasons instead of fairness. And there's also a fairness issue that cannot be addressed even if you have the same kind of accuracy within each of those groups.
Ready to connect.
Yes, I also feel that like the accuracy or the true positive or false positive rate, that could be dependent upon many other things. So only because some people are male or female and the accuracy is different, there could be different different other factors associated. But when somebody like in the media or the human perception is like, if they say that like 50% of all male applicants are the accuracy is high, and like for the female applicants the accuracy is low, then so even if maybe we can consider some overall low accuracy as well, but we need to consider the fairness concerns here. But yes, I feel the same. Like if we could propose some metric that also incorporates some other features, like all the features, that could be good.
Hi, this is Wei from computer science. Fairness comes with a set of metrics. Do you think it is easy to integrate those metrics into the goal of optimizations?
Professor Wei, yes, I think some metrics can be integrated. I also tried some of these. So basically, optimization is possible, but optimization should be class specific. Like if we try to optimize the true positive rate, I should optimize true positive rate for all the classes in my protected attribute. So I should try to optimize true positive rate for male and female at the same time, so that their difference in true positive rates become less. So to answer your question, yes, I think it's possible, but it's more important to consider different classes while optimizing the metrics.
Thank you. One more question. Can you provide more insights regarding why some of the model, when it's more accurate, it's less fair? I think you provide an example showing different optimization goals can lead to different fairness, but does different optimization goals necessarily affect accuracy? So is it a trend or observation that you see often, that more accurate leads to less fair?
Yes, I have found a trend that more accurate, less fair in many cases, but this is not always the case. I mean, there are more examples for that, but there are also a few examples where I have found that it is fair and accurate at the same time. But I think when we have applied the mitigation algorithms, we have found that many mitigation algorithms which have been most successful, like the post-processing algorithms, they have provided us a very fair decisions, but they have lost a lot of accuracy. So the most successful ones in the mitigation algorithms are losing accuracy, and some of the mitigation algorithms which are not so much successful like others are somehow retaining the accuracy. So sometimes we need to care for we need to look at the trade-off between accuracy and the performance and choose the mitigation algorithms carefully. Like for example, if we look at the Titanic models, if we always choose the most successful algorithm, that is the reject option classification, that might not help. Sometimes choosing the second best, like this is the rank of all the mitigation algorithms. So O represents the reject option, A represents the adversarial debiasing. So you can see the A is the adversarial debiasing is the second most successful algorithm. So maybe A is having more accuracy than O. So using the second best mitigation algorithms could be the most fruitful one.
Interesting, thank you. And the last, just very quick clarification question. So all those models, I see random forests. Is there any deep learning models are used in the evaluation?
No. So in this study, we only found the data science tasks that work on classification tasks, but and we did not find much work on the deep learning models, the fairness of deep learning models yet. But we are currently thinking about those different other models other than classification models as well.
Thank you.
Yep.
Thank you, everybody. Thank you, Sumon, for the talk.
Yeah. Thank you, Professor.
If you have any additional questions, of course, Sumon is going to be attending the future TADS meetings, and he can provide his email address as well for future questions. Thanks, everybody, for attending. I would just ask the POS committee members to stay at this point. Thank you, everybody, and have a good rest of the day.